Hi everyone, I'm Nick Sharp, and this is DiffusionNet, Discretization Agnostic Learning on Surfaces. Work with Souhaib Attaiki, Keenan, and Max Ovsjanikov. To cut straight to the chase, DiffusionNet is about learning functions on surfaces. And as the name suggests, the main idea of DiffusionNet is to use spatial diffusion along the surface as the main network operation. So whereas other past methods usually communicate along some graph of edges or along some neighbors in a point cloud, DiffusionNet instead uses the smooth action of diffusion as the way communication happens inside of the network architecture. The result is that the networks are very fast and highly accurate, and more importantly, they offer some new properties in terms of generalizing across different meshings, samplings, and resolutions of the shapes. And we'd argue that these are some really important properties which haven't been taken seriously enough in previous work. When we say learning on surfaces, we mean that we'll have some shape, like a mesh or a point cloud, and we want to learn a function which takes as input some features along the surface, like a value at each vertex of a mesh, and produces output predictions along that surface. This includes common tasks like segmentation, regression, or classification after taking a global mean. These learned functions depend on both the parameters theta that we fitted, as well as the shape on which we're learning. We're going to focus here on learning on individual, fairly well-resolved shapes, as opposed to, say, scene scale learning on raw sensor data. Of course, these networks apply in either case, but studying individual shapes really helps us drill down on the geometric implications of our network, and includes a whole lot of important tasks across visual computing as well. The challenge that really inspired us to start working on this problem is that of overfitting to sampling. I think this is something we've kind of brushed under the rug as a community, and which we're going to need to tackle head on as we integrate these methods into more and more applications. Here's an example of what I mean. This is an error plot for a recent state-of-the-art deep correspondence algorithm. The task is to predict correspondence against some other template shape which I haven't shown. On the left is a wireframe of the test mesh, and on the right is a shaded error plot of the model accuracy. And as we can see, the accuracy is all white because the model did essentially a perfect job. However, if we take the 3D mesh and we run it through a standard remeshing procedure, that same learned model all of a sudden starts outputting essentially total nonsense. The error is off the charts. So what happened here is that our network was supposed to learn a function of the shape, but actually it learned a function of the graph structure. It learned a function of the connectivity of the mesh that we ran it on. So as soon as we change the mesh connectivity, it can no longer do a good job. This issue is especially apparent for meshes, where it's common to train on template meshes or meshes that were generated by some particular meshing procedure. But the same problem also shows up on point clouds, where a network trained on uniformly sampled point clouds might output nonsense on some particular non-uniform sampling. What we're really seeking here is sampling agnostic learning, and we can contrast this with some kinds of invariance that have been widely studied in geometric machine learning. Permutation invariance means that the output of our network should not change when we, say, permute the vertices of a mesh, and at this point it's basically a solved problem. Rotation invariance means that the outputs of our network should not change as we rotate our input shapes. The good news here is that augmenting a dataset with random rotated versions of a shape is pretty effective, and also there's a wide range of principled architectures and formulations to tackle this property. So what we're asking for here is sampling invariance, that the output of our network should not change when we remesh a mesh or resample a point cloud. Now, really, instead of invariance, we're going to talk about being only sampling agnostic, because it's a bit too strict to say that the output shouldn't change at all when you resample. So instead, we're just saying it shouldn't change very much. Here, augmentation is really hard. There's no obvious strategy to, say, draw a mesh from the space of all possible meshes of a shape. And it's difficult to quantify what we're asking for via, say, some tidy mathematical formulation. All this is to say that sampling as invariance is a very unsolved problem. This is important to tackle because if we were, say, working on a physical simulation, this is a basic sanity check property we would expect our algorithms to have. We're just observing here that we should hold ourselves to the same properties in geometric machine learning, and this is really important in practice. So our diffusion networks will have three main ingredients. The first is a pointwise multilayer perceptron applied independently and identically at each vertex of the mesh or point in a point cloud. The next is our diffusion operation, which allows for spatial communication across the surface. And the last are some gradient features, which we use to expand the expressivity of our networks. Using diffusion for communication within our networks is really a big idea because past approaches have used complicated schemes involving, say, geodesic convolutions or pooling hierarchies or a whole space of other geometric operations. Although these are theoretically well posed, they can be difficult to evaluate on surfaces and are often sources of non-robustness in these models. Being able to use diffusion instead makes our networks very fast, very efficient, and very robust in practice. Diffusion is like a smearing out or blurring of a value over time. Given a scalar field defined along a surface, the rate of change of diffusion is given by the action of the Laplace operator. So down here at the bottom, we show an example of a value at a single point being diffused. In the limit of long time, diffusion will just give the average of the input values over the domain. Diffusion is kind of like a smooth mean pooling operation, to use the language of deep learning. The good news is that diffusion is essentially the most simple and basic PDE possible, and there are lots of great fast numerical methods to evaluate it. Diffusion is very much mathematically principled, standing on very rigorous foundations, and even on curved surfaces, diffusion is well defined via the Laplace-Beltrami operator from differential geometry, and has essentially the same properties that it does in the plane. These diffusion operations have been implemented and well studied on many geometric domains like meshes and point clouds. We even have robust versions for low-quality inputs. Our networks define a diffusion layer, which takes as input one channel of scalar data and diffuses it for some time t, producing a new, smoothed-out version of that channel. We'll do this diffusion independently for each channel. Rather than choosing this diffusion time manually, we're going to learn it as a continuous parameter of our networks, independently per channel. So this means that if we find a t-value near 0, then the spatial support is very local, whereas as t tends towards infinity, the support becomes totally global, eventually approaching a global mean. And this t-value, I want to emphasize, is automatically optimized as a continuous parameter during training. The spatial support of our networks is being learned as part of our standard training procedure. Here's a sneak preview of what happens. At the early layers of our network, these t-values tend to be small, local diffusion filters, whereas at the later layers of our network, they tend to be large, nearly global filters, just what we'd intuitively expect, but it emerges automatically during training. Now, you might be worried that doing away with traditional convolutions and using diffusion instead limits the expressivity of our networks. But in fact, we proved that the function space defined by diffusion followed by a pointwise perceptron includes all radially symmetric convolutions, so we're not actually losing anything by using simple and robust diffusion instead. This radially symmetric part is important because much like past work in this space, we want to go beyond radially symmetric filters. The solution we use here is quite simple. We construct extra features from the dot products of the spatial gradients of our existing feature channels and then append those as additional feature channels in our network. To give a little bit more detail here, in a tangent space about each point, we construct the gradient vectors of our existing feature channels, then apply a learned matrix A to the stacked vector of those tangent vector gradients, and then finally take dot products of the resulting tangent vectors after the linear transformation. I explained that real quick, but what's important is that this construction is indeed invariant to the choice of local tangent basis, as we would expect, and when we visualize the resulting filters, it really does take us beyond radially symmetric features. Something I haven't said too much about yet is how we evaluate diffusion. There are a lot of different ways you could evaluate diffusion, but we found it effective to use an eigendecomposition of the Laplace operator. This works well because in the eigenbasis, diffusion is just multiplying times a scalar. Our diffusion layer then just looks like a bunch of dense linear algebra after doing this precomputation to build the eigenbasis. It's important to be clear that although we're using an eigenbasis, DiffusionNet is not a spectral learning method, and the parameters of a DiffusionNet are not defined in terms of any particular set of eigenvectors or spectral basis. We're really just using this eigendecomposition as one numerical method to evaluate diffusion. There are many other numerical methods you could potentially use, and one other one we considered is a backwards Euler time step, although generally I recommend using this eigendecomposition in practice. The high-level takeaway from all of this is that although diffusion is indeed a smooth PDE along the surface, it's such a simple linear PDE that we're able to evaluate it using simple linear algebra operations, which are easy to implement in machine learning frameworks and can be differentiated through without any special treatment. Pulling all of this together, here's what our diffusion nets look like. Each diffusion net block takes as input a collection of channels of scalar data defined at each vertex or point in our shape, applies this spatial diffusion operation with learned time per channel, and then constructs these spatial gradient features I was just describing. These are all concatenated together and fed as the input to a multilayer perceptron applied independently at each point. Our full diffusion networks then just consist of many of these diffusion net blocks applied in sequence. This is pretty exciting. We don't need any pooling layers or other possibly difficult geometric operations because our spatial diffusion can already have global support if it's useful for the learning process. Remember, these networks learn maps between functions on the surface, so we're going to have to choose some input features in order to use them. We considered two main options: coordinate features, which are just XYZ positions. These are simple and completely encode a shape, but they are dependent on the rotation and translation you choose for your shape, which might be undesirable. Another option is to use heat kernel signatures as features, which are computed from the spectrum of the Laplace operator. These are multi-scale and purely intrinsic, both of which are valuable properties in practice. Of course, you can also use any problem-specific features you might have, such as color data defined along your surface. As we discussed earlier, we often expect that networks in geometric learning produce the same outputs when a shape is translated or rotated, so we're looking for invariance in our learning process. The good news is that these diffusion networks themselves are in fact rigid invariant. If you say translate the domain omega on which you're learning, you still have the exact same function in your diffusion net. So then the invariance of the whole learning process just depends on which features you choose as input. These XYZ coordinate features are not invariant, but we found that actually augmenting with random rotations was enough to get state-of-the-art results on many common benchmarks. Even better, you can use heat kernel signatures and get rotation and translation invariance for free with a purely intrinsic formulation. I don't want to waste too much time on particular benchmark numbers, but let's suffice to say that the scheme works very well in practice and gets state-of-the-art results across a variety of problems in visual computing, especially when mesh structure is available, and for problems when we want to learn and generalize from small training sets. Diffusion nets are also quite fast. On 15,000 vertex meshes, we can train at about 40 milliseconds per input, and training requires less than 3 gigabytes of memory usage. Our eigenbasis precomputation is performed once per input on the CPU and takes about 3 seconds on these meshes. Even better, we can scale up to some pretty huge meshes. Here's an example with 150,000 vertices. This is really the important property. Whereas a lot of past methods had to downsample to meshes with a few thousand vertices, we can easily run diffusion nets directly on full-size inputs, which makes them much easier to deploy in practice. And let's come back to this question of sampling invariance that we motivated at the beginning of the talk. Well, DiffusionNet is quite robust to resampling by default because it's built on top of the smooth, physically meaningful diffusion PDE. Here's an example again where we take this correspondence problem, trying to match the shape to some template which I'm not showing, and after remeshing the shape, the output of DiffusionNet only changes a very small amount. It retains almost all of its accuracy. And we really quantified this property by constructing a data set of meshes which have been sampled via a variety of different schemes, and show that really quantitatively, DiffusionNet is quite agnostic to discretization by default. Even better, this discretization agnostic property opens up some totally new capabilities. Not only can we train on template meshes and generalize to other connectivity, but we can even generalize across the discrete representation of our shapes. For instance, we can train on meshes and infer on point clouds using the exact same network weights, or operate on datasets which contain a mix of meshes and point clouds. This is all enabled because our diffusion nets are built upon smooth, physically meaningful operators like the Laplacians and gradients. Wrapping up here, in DiffusionNet, we showed how you can use the smooth, physically principled diffusion operation to build neural networks on surfaces. This approach has lots of benefits, including that it automatically generalizes across different discretizations, resolutions, and representations of your shapes. Even better, diffusion nets scale easily to high-resolution surfaces, which makes them easy to deploy in practice, and of course, they get really accurate results too. With that, I'll leave you, and you'll find some links here on the left to our open source implementation in PyTorch, the paper and data itself, and other materials. Thanks so much.